There is a universe inside you, not of stars and galaxies, but of sparks and wires, an intricate, living network that generates every thought, every feeling, and every action you will ever experience. It operates faster than a supercar and holds more connections than there are stars in our galaxy. This is your nervous system, the most sophisticated machine in the known universe, and we're about to uncover its most stunning secrets. If you're ready to be amazed by the body you live in every day, hit that subscribe button and let's get started. Let's begin with the sheer scale of it all. Your brain isn't just a lump of tissue, it's a city of 86 billion citizens. That's billion with a B. Each one of these citizens is a specialized cell called a neuron, the fundamental building block of your thoughts and consciousness. To put that number into perspective, there are more neurons in your head than there are people on Earth by a factor of more than 10. Each neuron is a tiny biological computer processing information and making decisions. And unlike many other cells in your body, most of the neurons you have now are the same ones you were born with. They are, for the most part, irreplaceable, making the network they form the most precious and unique structure you will ever own. It is the hardware on which the software of your entire life runs. But having 86 billion individual units isn't the truly mind-bending part. The magic happens in the connections. Each one of those neurons can form thousands of links with its neighbors, creating an impossibly dense web of communication. These connections are called synapses, tiny gaps where electrochemical signals leap from one cell to the next. How many are there? The current estimate is that the adult brain has around 100 trillion synapses. That's a 1 with 14 zeros after it, a number so vast it's hard to comprehend. To try, imagine our own Milky Way galaxy with its estimated 100 to 400 billion stars. Your brain contains at least 250 times more connections than our galaxy has stars. This colossal network is what allows for the complexity of human thought, memory, and emotion. It's not the number of cells, but the richness of their connections that creates the symphony of you. Now, imagine sending a message through a network that complex. You'd expect it to be slow, right? Lost in the traffic. But your nervous system is built for speed. The signals, or nerve impulses, that travel along your nerves are electrical charges, and they can move at breathtaking velocities. In the fastest insulated nerve fibers, these impulses can reach speeds of over 268 miles per hour, or about 120 meters per second. That's faster than a Formula One race car at full throttle. This incredible speed is what allows you to snatch your hand away from a hot stove before you've even consciously registered the pain. The signal for danger has already traveled from your finger to your spinal cord and back to your muscles, triggering a reflex action, all in a fraction of a second. Not all nerves are this fast, of course. Slower nerves handle things like the dull ache of a bruise, but the superhighways are reserved for urgent messages. What's the fastest thing you've ever done without thinking? Let me know your reflex stories down in the comments. So you have this massive, hyper-connected, super-fast network. But what powers it? It runs on electricity generated by your own body. While you're watching this, thinking, and even just existing, your brain is a biological power plant. It generates about 20 watts of electrical power. That's enough to light up a low-wattage LED bulb. It might not sound like a lot, but consider this. Your brain achieves this while making up only about 2% of your total body weight. Yet, this small organ is incredibly demanding, consuming a staggering 20% of your body's total oxygen and calorie intake. It's the most power-hungry organ you have. All of that energy is being burned to maintain your consciousness, regulate your body, and process the world around you. Your thoughts are, quite literally, electric. This electrical marvel is elegantly organized. Your nervous system is broadly divided into two major parts. First is the commander-in-chief, the central nervous system, or CNS. This consists of the brain and the spinal cord. It's the processing center where all the big decisions are made and information is integrated. Then you have the peripheral nervous system, or PNS. This is everything else, the vast network of nerves that branch out from the brain and spinal cord, reaching every single corner of your body, from the tips of your toes to the surface of your eyes. The PNS acts as the messenger network, carrying sensory information to the CNS and then relaying motor commands back out to the muscles and glands. If you laid all the nerves of your peripheral system end to end, they would stretch for more than 60,000 miles. That's enough to wrap around the entire planet more than twice. If you could enhance one part of your nervous system, your brain's processing power, or your body's reaction time, which would you choose and why? Drop your thoughts below. While the brain is the undisputed king of the nervous system, it has a fascinating and semi-independent partner that most people don't even know exists. Buried within the walls of your digestive system is the enteric nervous system, often called your second brain. This isn't just a catchy nickname. Your gut is lined with more than 100 million neurons. That's more than you'll find in your entire spinal cord. This intricate neural network is so complex that it can operate entirely on its own, managing the complex process of digestion without any input from the brain in your head. It controls muscle contractions, secretes enzymes, and keeps the whole system running smoothly. It also produces a huge amount of neurotransmitters, including about 95% of your body's serotonin, a key chemical for regulating mood. So that gut feeling you sometimes get, it might just be your second brain talking. Have you ever had a strong gut feeling that turned out to be right? Share your story. I'm genuinely curious to read them. The creation of this incredible system is perhaps its most amazing feat. How does this impossibly complex network get built from scratch? During early fetal development, your nervous system is constructed at a pace that defies belief. In the first few months of gestation, neurons are formed at an average rate of 250,000 per minute. That's nearly 15 million new brain cells every hour. It is the most intense and sophisticated construction project in the known universe, and it's all happening according to a genetic blueprint that has been refined over millions of years of evolution. These brand new neurons then have to migrate to their correct positions and begin the monumental task of wiring themselves together, forming that 100 trillion synapse network. What's the most complex thing you've ever built or created? It's humbling to compare that to your brain building itself before you were even born. From the sheer number of its cells to the blistering speed of its signals and the hidden brain in your gut, the nervous system is a masterpiece of biological engineering. We've only just scratched the surface of the electrical storm that powers your every moment. But what we've seen today reveals a fundamental truth. You are a walking, talking miracle of complexity. We've talked about the hardware, but what about the software? In the next chapter, we'll dive into how this system actually creates your reality, how it turns light into sight, air pressure into sound, and how it stores your most precious memories. If you found any of this as mind-blowing as I do, show your support with a like and make sure you're subscribed so you don't miss what's coming next. And just like that, with a single thought, you've commanded an entire universe. Not the one of stars and planets, but the one between your ears. It's a universe of staggering scale, and to truly appreciate it, we have to start with the population. You are currently hosting around 86 billion neurons inside your skull. That's not a typo, 86 billion. For a long time, scientists rounded that up to 100 billion, but a more precise count landed on this slightly smaller, yet no less mind-boggling number. To put that in perspective, the most generous estimates suggest there are about 100 billion stars in our Milky Way galaxy. You are walking around with a structure inside your head that contains nearly as many primary processing units as there are suns in our home galaxy. Each one is a living cell, firing, wiring, and keeping the incredible show that is you on the road. But if each of those 86 billion neurons is a star, then the real magic isn't in the stars themselves, but in the connections between them. This is where the scale goes from galactic to something else entirely. Each neuron can form thousands of links with others, creating a web of connections known as synapses. The total number of these connections is, frankly, almost beyond human comprehension. The best estimate? Somewhere around 100 trillion synapses. Some neuroscientists even place it closer to a quadrillion. That's a 1 with 15 zeros after it. If you were to count every single one of these connections, 1 per second, it would take you over 30 million years to finish. This intricate network is what allows for the complexity of thought, memory, and emotion. It's not just a collection of cells, it's an impossibly dense, interconnected web that makes the entire internet look like a child's toy. Now, imagine sending a message across that impossibly complex network. How long would it take? You'd probably expect some delay, a bit of biological lag, but you'd be wrong. The information zipping through your nervous system travels at truly astonishing speeds. The fastest nerve impulses, typically those carrying signals for touch or muscle control, travel along specialized, insulated nerve fibers called myelinated axons. These signals can rocket along at speeds of up to 268 miles per hour. That's faster than a Formula One race car at full throttle. This incredible speed is why you can snatch your hand back from a hot surface before you've even consciously registered the pain. Of course, not all signals are in such a hurry. Slower, unmyelinated fibers, which often transmit a dull, throbbing pain, might only clock in at about 1 or 2 miles per hour. Your nervous system, it turns out, has both a supercar and a casual walking pace for sending its messages. Running a biological supercomputer of this magnitude, with its galactic scale and race car speeds, requires a phenomenal amount of power. And this is where one of the most incredible paradoxes of human biology comes into play. Your brain, which typically accounts for only about 2% of your total body weight, is the most energy-hungry organ you have by a long shot. It greedily consumes a staggering 20% of your body's total oxygen and calories. Think about that. A tiny fraction of your mass is demanding a fifth of all your resources. This is true even when you're resting or sleeping. Your brain is always on, maintaining that incredible electrical potential across trillions of connections. It's the reason why intense concentration can leave you feeling physically exhausted. Your brain has literally been burning through fuel at an incredible rate. The sheer scale of this system isn't just about the number of cells, it's also about its physical reach. If you could carefully unravel every single nerve from your body, from the thick spinal cord to the tiniest nerve endings in your fingertips, and lay them all out in a single line, the total length would be almost unbelievable. Scientists estimate that the combined length of all the motor and sensory nerves in an average adult human is approximately 100,000 kilometers. That's over 60,000 miles. This internal wiring is long enough to circle the Earth almost 2.5 times. Every part of you is connected by this vast, sprawling network, ensuring that no sensation is missed and no command from the brain goes undelivered, no matter how distant the destination. And that delivery system is not a one-way street. We often think of the brain as a command center, barking orders out to the body, but that's only half the story. Your nervous system is in a constant state of two-way communication. There are two primary types of nerve pathways. Efferent, or motor neurons, are the ones carrying signals away from the central nervous system, the brain and spinal cord, telling your muscles to contract or your glands to secrete. But just as important are the afferent, or sensory neurons.
These are constantly sending a flood of information towards the central nervous system, reporting on everything from the temperature of the room and the texture of the object you're holding to the position of your limbs in space. It's a perpetual, perfectly synchronized conversation, a beautiful dance of outgoing commands and incoming status reports. For centuries, it was believed that you were born with all the brain cells you would ever have, and that once they were gone forever. But we now know this isn't true, thanks to the discovery of a process called neurogenesis. In specific areas of the brain, most notably the hippocampus, which is crucial for learning and memory, new neurons are being generated throughout your entire adult life. Activities like learning a new skill, engaging in aerobic exercise, and even navigating new environments can stimulate the birth of these new brain cells. It's a profoundly hopeful discovery, suggesting our brains are not static, decaying organs, but dynamic, living structures capable of growth and renewal. What's one new skill or piece of information you've learned recently? Let me know in the comments. You might have literally grown your brain in the process. This brings us to one of the strangest and most fascinating truths about the entire nervous system. The brain, the very organ that processes and interprets every single pain signal from your entire body, the sting of a cut, the ache of a muscle, the burn from a flame, has no pain receptors of its own. It feels nothing. This is why surgeons can perform brain surgery on patients who are wide awake without them feeling any pain from the procedure on the brain itself. The brain is the master interpreter of pain, the seat of the experience of suffering, yet it is completely numb to its own physical state. It is the silent, unfeeling observer in the control room, diligently processing distress signals from every corner of its kingdom, without ever being able to feel that pain firsthand. What if I told you the most complex, most powerful, and most mysterious object in the known universe isn't floating in the cold emptiness of space, but is sitting right between your ears? It weighs just 3 pounds, feels like soft tofu, yet it holds every memory, every dream, and every thought you've ever had. Welcome back to our deep dive into the human body's command center. Today, we're unlocking the secrets of the brain itself. If you're ready for your mind to be blown by, well, your own mind, make sure you've hit that subscribe button, because we are diving straight into the astonishing. You might think that an organ responsible for processing every sensation would be incredibly sensitive itself, but here's a startling truth. Your brain feels no pain. That's right, it has no pain receptors or nociceptors of its own. This is why neurosurgeons can perform procedures on patients while they are awake, probing and operating on brain tissue without causing any direct physical pain to the organ itself. The excruciating agony of a headache doesn't come from your brain, but rather from the nerves, blood vessels, and muscles that surround it. The brain is the master interpreter of pain signals from all over your body, from a stubbed toe to a paper cut, but it remains blissfully unaware of any direct injury to itself. It's like a world-class news anchor reporting on global catastrophes from inside a soundproof studio, processing all the information without ever feeling the impact firsthand. So if it can't feel, how does it think? The answer is electrifying. Your brain is a low-voltage biological generator. At any given moment, the combined activity of its billions of neurons produces enough electricity to power a small, low-wattage LED light bulb, somewhere between 10 to 23 watts. Every single thought, every memory recalled, every command sent to your muscles is an electrical impulse firing from one neuron to another across a synapse. So that classic cartoon image of a light bulb appearing over someone's head when they have an idea, it's not entirely fiction. You are literally having an electric thought. This constant, quiet hum of electrical energy is what makes you, you. All of that electrical power has to come from somewhere, and your brain is incredibly greedy for resources. Despite making up only about 2% of your total body weight, it is the single most demanding organ you have. It greedily consumes a staggering 20% of all the oxygen you breathe and 20% of all the calories you ingest. This energy is required 24/7, even when you're asleep. This incredible energy drain is to fuel those constant electrical impulses that maintain your basic life functions, process sensory information, and power your thoughts. It's a high-performance engine that never, ever shuts off. What's the most surprising brain food you've ever eaten that you felt actually made a difference? Drop your go-to snack for a big study session in the comments below. That energy is used to maintain an infrastructure of connections so vast it defies easy comprehension. Your brain contains roughly 86 billion neurons, which is an impressive number on its own. But the real magic isn't in the number of cells, but in how they connect. Each neuron can form thousands of links with other neurons, creating a web of connections known as synapses. The estimated number of these synapses in an adult brain is around 100 trillion. To put that into perspective, there are more neural connections in your single 3-pound brain than there are stars in our entire Milky Way galaxy. It's a universe of complexity tucked inside your skull, a network so dense and intricate that we are only just beginning to map its outer edges. With a network that vast, you'd expect an equally impressive storage capacity, and you would be absolutely right. When we talk about computer memory in gigabytes or terabytes, we're talking about child's play compared to the human brain. Scientists estimate the brain's storage capacity to be somewhere around 2.5 petabytes. That's a million gigabytes. If your brain were a digital video recorder, it could hold 3 million hours of high-definition television shows. You would have to leave the TV running continuously for more than 300 years to fill up that much space. Unlike computer memory, it's not just static storage, it's dynamic, interconnected, and constantly being updated. If you could instantly download one new skill directly into your brain, what would you choose to learn in a second? I'd love to see what you'd pick in the comments. This immense network isn't fixed in place like the circuits on a computer chip. Your brain is constantly changing, remodeling, and reorganizing itself in response to your experiences. This remarkable ability is called neuroplasticity. Every time you learn a new fact, practice a skill, or create a memory, you are physically altering the structure of your brain. New neural pathways are formed, and old ones are strengthened or weakened. This is how we learn to play a piano, speak a new language, or recover from brain injuries. The brain can reroute functions from a damaged area to a healthy one, like a city's traffic control system creating detours around a roadblock. Your brain isn't just a processor, it's a living sculpture, and you are the artist, shaping it with every single thing you do and learn. Now, you might think all this learning and rewiring primarily happens when you're awake and focused. But some of the brain's most critical work happens when you're completely unconscious. Your brain is often far more active when you're asleep than it is during many of your waking hours. While you're dreaming, your brain is busy consolidating memories, transferring important information from your short-term memory to long-term storage. It's also hard at work clearing out toxins that build up during the day, essentially taking out the metabolic trash. So, while you might feel like your brain is off when you're sleeping, it's actually running a highly active, crucial maintenance and filing program that is absolutely vital for learning, memory, and overall cognitive health. Ever had a dream so vivid it felt more real than reality? Tell me about the wildest dream you can remember down below. Another fascinating aspect of your brain's structure is its incredible water content. While it's the seat of our consciousness and identity, about 75% of the brain's mass is simply water. This high water content is crucial for maintaining the delicate balance of electrolytes needed for those electrical impulses to fire properly. Even slight dehydration can have a significant impact on your cognitive functions, leading to issues with memory, attention, and decision-making. It's a powerful reminder that this supercomputer of an organ is still a biological machine, fundamentally reliant on the most basic substance for life. It's not just your body that gets thirsty, your brain does too. And while it's processing all that information, it does so at breathtaking speeds. Information can travel through different types of neurons at different velocities, but the fastest signals zip along at over 268 miles per hour. This is thanks to a fatty substance called myelin, which acts as an insulator around the axons of neurons, allowing the electrical signal to leap from point to point instead of flowing smoothly. This process, called saltatory conduction, is what allows you to, for instance, instantly pull your hand away from a hot stove before your brain has even consciously registered the pain. It's a biological superhighway that allows for reflexes and thoughts that move faster than a Formula One race car. What's the fastest you've ever had to think on your feet to get out of a tricky situation? Share your story in the comments. From its shocking immunity to pain, to its galaxy of connections and the sheer speed of its thoughts, the brain remains our greatest frontier. It builds our reality, stores our past, and imagines our future, all while running on the power of a dim light bulb. And the most incredible part? We've only just begun to understand its deepest secrets. What if I told you that the vibrant, solid world you perceive around you right now is just an illusion? A stunningly detailed, high-definition hallucination cooked up by your brain. Because that's exactly what it is. Your sensory systems aren't windows to the world, they're data collectors, and your brain is the master artist that paints your reality. So let's pull back the curtain on how it creates the show. We think of our eyes as separate cameras feeding information to our brain, but the truth is far more intimate. Your retina, the light-sensitive layer at the back of your eye, isn't just connected to the brain, it is, quite literally, brain tissue. During fetal development, a part of the developing brain, the diencephalon, pushes outward to form the optic cups, which eventually become your retinas. This means that when light hits your eye, it's not just hitting a sensor, it's directly interacting with an exposed piece of your central nervous system. These retinal cells perform complex initial processing, filtering, and organizing visual data before it even begins its journey down the optic nerve. So, in a very real sense, you begin seeing with your brain before the signal even leaves your eyeball. Now, because this piece of the brain needs a way to send its massive data stream back to headquarters, there's a physical exit point for the optic nerve. This creates a hole in the retina of each eye, a spot with 0 photoreceptor cells. This is your physiological blind spot. Yet you never notice it. You don't see a black hole in your vision as you look around. Why? Because your brain is a masterful editor. It takes the information from your other eye and the visual data surrounding the blind spot and flawlessly photoshopping the gap in real time. It guesses what should be there with incredible accuracy, creating a seamless, uninterrupted visual field. Your brain actively constructs a complete picture from incomplete data, a trick it performs every single second you have your eyes open. From the silent, seamless editing of our vision, let's switch gears to the world of sound, a world interpreted by some of the most delicate and remarkable machinery in the human body. Inside your middle ear are the 3 smallest bones in your entire skeleton, the malleus, incus, and stapes, often called the hammer, anvil, and stirrup. Lined up, all 3 could sit comfortably on the tip of your pinky finger, but their size betrays their power. When sound waves make your eardrum vibrate, these tiny bones act as a mechanical amplifier, a perfect lever system that increases the force of those vibrations by more than 20 times before transmitting them to the fluid-filled inner ear. This amplification is crucial. It's what allows you to hear the faintest whisper and the most subtle shifts in tone. Without these three minuscule bones, the world would be a muffled, distant place. But hearing isn't just about amplifying sound, it's also about filtering it. Imagine being at a loud party. Music is blasting, people are shouting, glasses are clinking. Yet somehow you can tune all of that out and focus on the single voice of the person you're talking to. This incredible ability is known as the cocktail party effect, and it's a testament to your brain's sophisticated noise cancellation software. Your auditory cortex doesn't just passively receive sounds, it actively sorts, prioritizes, and suppresses them. It uses cues like the direction of a sound and the unique pitch of a voice to create a spotlight, enhancing the sounds you want to hear while pushing the rest into the background. It's a constant, subconscious process of signal versus noise, managed entirely by your nervous system. What's the most persistent sound your brain has to filter out just for you to focus? Tell me in the comments. I'd love to know what your personal cocktail party sounds like. Now, let's turn our attention inward to a sense you're using right now without even realizing it. It's often called our sixth sense, but it's far more fundamental than any psychic power. It's called proprioception. Close your eyes and touch your finger to the tip of your nose. Easy, right? But how did you do it? You didn't see your finger or your nose, you felt their position in space. That's proprioception. Specialized nerve endings in your muscles, tendons, and joints are constantly sending a flood of information to your brain, reporting the angle of your elbow, the tension in your calf, the rotation of your hip. Your brain integrates this data into a dynamic 3D model of your body, allowing you to move smoothly and coordinate actions without constant visual feedback. It's the silent autopilot that lets you walk, type, or drink a coffee while looking elsewhere. The power of this internal body map becomes hauntingly clear in the phenomenon of phantom limbs. When a person loses a limb, the sensory map for that arm or leg in the brain doesn't just disappear. The dedicated neural real estate that once received signals from that limb remains active, but it's now silent, deprived of its input. Sometimes, this silent area of the brain can spontaneously fire, or signals from neighboring brain regions can bleed over into it. When this happens, the person can feel vivid, undeniable sensations, an itch, a pain, a feeling of warmth in the limb that is no longer there. This isn't imagination. It's real neural activity creating a real sensation. It's powerful proof that our experience of our body is generated not in the body itself, but within the intricate maps of the brain. This idea that perception happens in the brain, not the sense organ, is perhaps most beautifully illustrated by our sense of smell. You don't actually smell with your nose. Your nose is the hardware containing millions of olfactory receptor neurons that trap odor molecules. But the experience of smelling, the recognition of freshly cut grass or baking bread, happens much deeper inside your brain. The olfactory bulb, which processes these signals, has a direct superhighway-like connection to the brain's most primitive and emotional centers, the amygdala, which processes emotion, and the hippocampus, which is crucial for memory formation. This unique wiring is why no other sense can trigger memories and emotions with such sudden, gut-wrenching power. A single scent can bypass conscious thought and transport you decades back in time, all because its pathway is hardwired directly into the heart of your memory and emotional core. Your brain isn't just identifying a smell, it's reliving a moment. So our brain builds our entire reality from the electrical whispers of our senses, filling in the gaps, filtering the noise, and linking it all to our deepest emotions and memories.
But how does it then command our bodies to move and act within that handcrafted world? The story of how a single thought becomes a physical action is where we're heading next. Imagine a highway that builds its final off-ramp when you're just 4 years old, even as the country around it continues to grow for another decade. That strange highway exists inside every single one of us. We're talking about the spinal cord, the master communication channel that does far more than just ferry messages back and forth.
It's a structure of profound intelligence and surprising secrets. So let's journey down the spine, because this biological skyscraper holds some of the nervous system's most elegant and mind-bending truths. And it all begins with that strange growth pattern. While your vertebral column, the bony fortress protecting it, continues to grow until you're a late teen, your actual spinal cord stops lengthening around the age of 4 or 5. This creates a fascinating mismatch. As your backbone elongates, the spinal cord doesn't keep pace, meaning in an adult, it doesn't run all the way to the bottom of the spine. It typically ends around the first or second lumbar vertebra in your lower back. This anatomical quirk is precisely why a spinal tap or lumbar puncture is performed so low down. Doctors can safely insert a needle to sample cerebrospinal fluid without any risk of damaging the delicate cord itself, because at that level, the cord simply isn't there anymore. It's a clever exploitation of our own developmental timeline. But don't mistake the spinal cord for a simple, passive cable. It has a mind of its own. Buried within its gray matter are incredible networks of neurons called central pattern generators, or CPGs. These are essentially mini-brains that handle complex, rhythmic movements without needing constant step-by-step instructions from your actual brain. Think about walking. You don't consciously command left foot forward, right arm swing, right foot forward, left arm swing. You just decide to walk, and it happens. That's your spinal CPGs taking over. They generate the basic rhythm and muscle coordination for locomotion automatically. The brain's job is simply to give the start and stop command and to make adjustments for navigating obstacles or changing speed. This frees up immense processing power in your brain, allowing you to walk while talking, thinking, or looking at the world around you. It's an incredible example of distributed intelligence, a silent symphony of coordination happening just below your conscious awareness. This silent symphony even affects your height on a daily basis. You are measurably taller in the morning than you are in the evening, sometimes by as much as a full inch. It's not your bones shrinking, it's the 23 cartilaginous discs nestled between your vertebrae. These discs are like little jelly-filled cushions, primarily made of water. Throughout the day, as you stand and move around, the constant pressure of gravity squeezes water out of them, causing them to compress slightly. But when you lie down to sleep, the pressure is off. Over several hours, these discs rehydrate and expand back to their full size, pushing your vertebrae slightly further apart and adding that extra bit of height. It's a temporary boost, but a fascinating daily reminder of the spine's dynamic, living nature. What's the first thing you do every morning? I'm curious to see how many people have a routine that takes advantage of that extra morning height. Let me know in the comments. Considering the monumental task of carrying all the nerve signals for your entire body and the daily compression it endures, you might imagine the spinal cord to be a thick, robust rope. But the reality is shockingly different. For most of its length, the adult spinal cord is only about as thick as your little finger, roughly ½ an inch in diameter. It's this incredibly slender, delicate column of tissue that is responsible for connecting your brain to virtually everything below your neck. Packed into this tiny space are millions of nerve fibers, organized with breathtaking precision into pathways that control movement, sensation, pain, temperature, and more. It's a testament to biological efficiency, a superhighway of information that is more compact and powerful than any fiber optic cable ever engineered. Its fragility is why spinal injuries can be so devastating, But its slender design is a marvel of biological engineering, and this slender column is capable of some serious acrobatics. While it feels rigid, the human spine is astonishingly flexible. If you were to bend forward as far as possible, the vertebral column has the potential to curve enough to form nearly 2/3 of a complete circle. This incredible range of motion is thanks to the combined small movements of each individual vertebra and its cushioned disc. No single joint is bending dramatically, but the summation of all those tiny adjustments allows for the fluid, graceful movements of a gymnast or a dancer. It allows us to bend, twist, and arch in ways that seem to defy the logic of a central support structure. This combination of robust strength for protection and incredible flexibility for movement is one of the spine's greatest evolutionary triumphs. Peeling back the layers even further, if you could look at a cross-section of the spinal cord, you'd find a secret, microscopic feature right at its very heart. Running down the exact center of the cord is a tiny, fluid-filled channel known as the central canal. It's so small it's often invisible to the naked eye. This canal is a direct remnant from our earliest moments as an embryo, when our entire nervous system was just a simple hollow tube called the neural tube. As we developed, this tube sophisticated into the brain and spinal cord, but a trace of that original hollow space remains. This central canal is lined with the same type of cells that line the ventricles of the brain, and it's connected to the entire cerebrospinal fluid system, helping to circulate this vital, cushioning fluid throughout the central nervous system. It's a hidden river, a ghost of our own creation story, flowing silently through the core of our being. Finally, we arrive at the very bottom, where the solid spinal cord ends and something truly unique begins. Because the nerves for your lower body still need to exit the spine at the correct lower levels, they have to travel down past the end of the cord before they can leave the vertebral column. This creates a stunning structure called the cauda equina, which is Latin for horse's tail, and it looks exactly like one. It's not a solid cord anymore, but a beautiful, flowing bundle of individual nerve roots that dangle down through the spinal canal before branching off to supply the legs, feet, bladder, and bowels. This is the collection of nerves that controls everything from kicking a ball to the subtle sensations on the soles of your feet. This elegant, tail-like structure is the grand finale of the spinal cord, the point where the central superhighway frays into the countless local roads that animate the lower half of our world. What if I told you that inside your head right now is a communications network so vast and complex it makes the entire global internet look like a toy? We're not talking about wires and fiber optics. We're talking about the biological machinery that creates every thought, feeling, and action you've ever had. Get ready to plug in, and if you want to keep your mind blown, make sure to hit that like and subscribe button. Today, we're exposing the lightning-fast world of your neural networks. Let's start with the fundamental spark of all thought, the action potential. This isn't just a vague electrical fizz, it's a precisely controlled explosion of electrochemical energy. When a neuron decides to fire, it opens tiny gates in its membrane, allowing positively charged sodium ions to flood in. This flips the neuron's internal charge from negative to positive in less than a millisecond, creating a wave of electricity that races down its axon. This isn't a simple current like in a copper wire. It's a self-propagating cascade, a domino effect of ion channels opening and closing, ensuring the signal travels without losing any strength, whether it's going a millimeter across your cortex or a full meter down your spinal cord to your big toe. Now, you might think that signal travels at the speed of light, but it's actually a bit more complicated and a lot more clever. The raw speed of an action potential in an uninsulated nerve fiber is surprisingly slow, sometimes as pokey as 2 miles per hour. To solve this speed issue, your nervous system developed a brilliant biological hack, myelin. Specialized cells wrap your neuron's axons in a fatty, insulating sheath, much like the plastic coating on an electrical wire. But this insulation has tiny, regularly spaced gaps. Instead of flowing smoothly, the electrical signal literally leaps from one gap to the next in a process called saltatory conduction. This biological trampolining allows nerve impulses to rocket along at speeds up to 268 miles per hour, turning a leisurely stroll into a supersonic flight and enabling the rapid-fire processing required for everything from dodging a stray ball to understanding this very sentence. But what happens when that supersonic signal reaches the end of the line? This is where the real magic begins. Neurons don't actually touch each other. There's a microscopic gap between them, a tiny chasm called the synapse, about 20 nanometers wide. For the signal to cross this gap, the electrical impulse is converted into a chemical one. The sending neuron releases a burst of molecules called neurotransmitters into the synapse. These molecules are like tiny chemical keys floating across the gap. They then dock with specific receptor sites on the receiving neuron, which act like locks. When the key fits the lock, it triggers a new electrical signal in the next neuron, continuing the message. This entire, impossibly intricate process of conversion from electricity to chemistry and back again happens in under a millisecond. And that chemical message isn't just a simple on or off signal. Your brain uses over 100 different types of neurotransmitters, each with a unique shape and function. Some, like glutamate, are excitatory, revving the next neuron up and making it more likely to fire. Others, like GABA, are inhibitory, calming the next neuron down and making it less likely to fire. This constant push and pull, this delicate balance of green lights and red lights across trillions of synapses is what allows for the nuance of thought. It's the difference between a gentle touch and a painful jab, the reason you can focus on one conversation in a loud room, and the source of your every mood and emotion. The complexity is astounding. Which of your daily activities do you think requires the most complex balance of these neural signals? Drop your best guess in the comments below. This system of signals and gaps creates a network of almost unimaginable scale. The average adult brain contains around 86 billion neurons. That's more than 10 times the number of people on Earth. But the truly mind-boggling number isn't the neuron count. It's the number of connections or synapses. Each of those 86 billion neurons can form thousands of connections with its neighbors. The result is a network with an estimated 100 trillion to potentially 1 quadrillion synaptic connections. To put that into perspective, there are more connections in a single cubic centimeter of your brain tissue than there are stars in our entire Milky Way galaxy. Every memory you hold and every skill you've learned is encoded within the unique pattern of these countless connections. So, with a network that vast, how does your brain keep from being a chaotic mess of crossed signals? It actively prunes itself. During childhood and adolescence, your brain undergoes a process called synaptic pruning, where it systematically eliminates weaker or less used synaptic connections while strengthening the ones that are used frequently. It's a literal use it or lose it principle hardwired into your biology. This process is absolutely vital for learning and development as it streamlines the brain's networks, making them more efficient and specialized. It's how a baby's brain, which starts with a surplus of connections, can fine-tune itself to recognize its parents' faces, understand language, and master complex motor skills like walking. Your brain literally sculpts itself based on your experiences. And that sculpting process never truly stops. This leads us to one of the most profound truths of neuroscience. Your brain's communication network is not static. It is constantly remodeling itself in response to your experiences, a property known as neuroplasticity. Every time you learn a new fact, practice a skill, or form a new memory, you are physically altering the wiring of your brain. The connections between specific neurons become stronger and more efficient, making it easier for them to communicate in the future. This is why practice makes perfect. You're not just training your muscles, you're literally carving a more efficient pathway in your neural network. This incredible adaptability means your brain is a dynamic, living web of communication that is constantly being rewoven by the tapestry of your own life. Did you remember to beat your heart just now? What about taking your last breath or adjusting your body temperature? Of course not. And yet, an unseen commander inside you is orchestrating all of it, every single second, without you ever having to think about it. Welcome to the world of your body's incredible autopilot. This silent, tireless network is your autonomic nervous system, and it's arguably the most critical system for your survival. It works through a constant, delicate balancing act between two opposing forces, like a master driver with one foot on the gas and the other on the brake. One side is the sympathetic nervous system, your body's accelerator, and the other is the parasympathetic nervous system, your precision brake and cruise control. Together, they form a dual command system that finely tunes your internal state to match the external world. When you're exercising, your sympathetic side takes over, increasing heart rate and blood flow. When you're relaxing after a meal, the parasympathetic side engages, slowing things down and focusing on digestion. This isn't a simple on-off switch. It's a dynamic dance, a constant push and pull that maintains the perfect internal equilibrium, known as homeostasis, allowing you to live, breathe, and function without ever consciously issuing a single command. But what happens when that balance needs to be shattered in an instant? That's when your fight or flight response performs a total body takeover. When your brain perceives a threat, whether it's a speeding car or a stressful work email, your sympathetic nervous system doesn't just tap the gas, it slams it to the floor. It triggers a system-wide cascade of physiological changes designed for one thing: immediate survival. Your pupils instantly dilate to let in as much light and information as possible. Your airways open up to maximize oxygen intake. Your heart pounds, sending oxygenated blood surging not to your stomach, but directly to your major muscle groups. Your liver dumps glucose into your bloodstream for a massive instant energy boost. Even your blood itself changes, with clotting factors increasing in preparation for potential injury. It's an ancient, powerful, and all-encompassing override that transforms you into a peak performance survival machine in a fraction of a second. Once the perceived danger is gone, the emergency override is disengaged, and a different kind of hero steps in. Your rest and digest system is your body's master healer and chief recovery officer. The parasympathetic nervous system doesn't just put the brakes on the chaos. It actively initiates profound processes of restoration and conservation. Your heart rate slows, your blood pressure drops, and blood flow is redirected back to your core, firing up your digestive and metabolic processes. But its job is far more intricate than just chilling you out. This is the state where your body performs its most critical long-term maintenance. It's when your cells repair themselves, your tissues rebuild, and your body shores up its resources for the future. Activating this system through things like deep breathing or meditation isn't just about feeling calm. It's about giving your body the explicit green light to heal and strengthen itself from the inside out. What's your go-to way to activate that rest and digest mode? Let us know your best relaxation hack in the comments. This autonomic control extends to some truly bizarre and ancient reflexes, some of which seem to make no sense today. Take goosebumps, for instance. That strange prickling of the skin you get when you're cold, or sometimes even scared, is a direct command from your sympathetic nervous system. It's an evolutionary relic known as piloerection. Tiny muscles called erector pili, attached to the base of each hair follicle, contract simultaneously, causing the hairs to stand on end.
For our much hairier ancestors, this served two key survival purposes. First, it made them look bigger and more intimidating to a potential predator. Think of a cat puffing up its fur. Second, the erect hairs would trap a layer of air close to the skin, creating a natural layer of insulation against the cold. For us, with our relatively sparse body hair, it does neither of these things effectively. Yet the ancient neural circuit remains, a fossilized reflex from a time when survival was a much hairier situation. From the surface of our skin, let's travel deep into our core, to a place run by a shockingly complex and independent intelligence. Believe it or not, you have a second brain located in your gut. Officially called the enteric nervous system, this intricate mesh of neurons is embedded in the walls of your gastrointestinal tract, from your esophagus all the way down to your colon. And it is vast. It contains over 100 million neurons, more than are found in your entire spinal cord or your peripheral nervous system. This second brain is so sophisticated and so capable that it can, and often does, operate entirely independently of the brain in your head. It manages the incredibly complex dance of digestion, controlling muscle contractions, regulating acid and enzyme secretions, and monitoring nutrient absorption, all without any conscious input or even oversight from the central nervous system. It's the only part of your body, besides your brain, that can function as its own independent command center. But this second brain isn't completely isolated. It's connected to your main brain by a massive information superhighway, the vagus nerve. This is the longest and most complex of the cranial nerves, wandering from the brainstem down through the neck and into the chest and abdomen, touching nearly every major organ along the way. It is the primary channel for your parasympathetic or rest and digest system. But here is the most astonishing part. This superhighway is not a one-way street, and the traffic is heavily skewed in one direction. An estimated 80 to 90% of the nerve fibers in the vagus nerve are dedicated to communicating from the gut to the brain. This means your gut is constantly sending a massive stream of information upstream, profoundly influencing your mood, your stress levels, and even your thoughts. That gut feeling you get isn't just a metaphor, it's a real neurobiological signal originating from your second brain. Finally, there's one part of the autonomic nervous system's work that you can see with your own eyes, if you know where to look. Your pupils are a direct, real-time window into your internal state. While their primary job is to control the amount of light reaching the retina, their size is dictated by that constant push and pull between your sympathetic and parasympathetic systems. When you're calm and relaxed, the parasympathetic system dominates, constricting the pupils. But in a state of arousal, fear, or excitement, the sympathetic system takes over, causing them to dilate widely to capture more visual information. It's so sensitive that researchers have found pupil dilation is a reliable indicator not just of emotional arousal, but also of intense mental effort. When you're concentrating on a difficult math problem or trying to remember a name, your pupils widen. They are an honest, involuntary broadcast of your cognitive and emotional engagement with the world. This incredible autopilot, from your gut to your eyes, keeps you alive and responding moment to moment. But how do these signals travel such vast distances at such incredible speeds? That's where things get truly electric. We've explored the high-speed highways of our nervous system, but now we venture deeper, into the very architecture of the mind itself, the place where thoughts are not just sent, but born. Tucked away in the quiet moments when you think you're doing nothing at all, your brain is running one of its most important programs. This is the default mode network, or DMN, a vast, interconnected web of brain regions that hums with activity when you're daydreaming, recalling memories, or imagining the future. It's your brain's internal narrator. When you're focused on a task, the DMN quiets down. But the second your mind wanders, it springs back to life, weaving together your past,
present and future into a continuous sense of self.
This network is so fundamental that its disruptions are linked to conditions from depression to Alzheimer's, proving that even our quietest moments of reflection are the product of a powerful and finely tuned neural machine. It's the ghost in the machine, constantly defining who you are, even when you're not paying attention.
This internal world mapping doesn't just apply to our sense of self. Our brain literally builds maps of the world around us. Deep within the hippocampus, a structure crucial for memory, reside spectacular neurons known as place cells. In 2014, the discovery of these cells and their cousins, grid cells, won the Nobel Prize, and for good reason. As an animal or a person moves through an environment, specific place cells fire to mark their precise location. Think of them as neural thumbtacks on a cognitive map. But it gets even more incredible. Nearby, grid cells fire in a stunningly geometric hexagonal pattern, providing a coordinate system, like latitude and longitude lines, for the place cells to operate on. Together, they create a rich, dynamic GPS system in your head, allowing you to navigate complex spaces, remember shortcuts, and know where you are in relation to everything else. This internal atlas is so precise, it remaps and adapts to new environments within minutes, constantly updating your position in the world. But this internal map isn't just about geography, it's also about emotion. Every location has a feeling attached to it, thanks to another deep structure, the amygdala. This almond-shaped cluster of neurons is the brain's fear and emotion processing center, and it works hand in hand with the hippocampus to create what are known as fear memories. When you have a frightening experience, the amygdala goes into overdrive, tagging the memory with a powerful emotional warning signal. The hippocampus then stores the contextual details, where you were, what you saw, what you heard. The connection between them is so strong that returning to that location, or even just seeing a similar-looking place, can trigger the amygdala to reactivate that fear response, making your heart pound all over again. This ancient survival mechanism is brutally efficient, ensuring we don't forget life-threatening situations. It's the reason why a single, terrifying event can create a phobia that lasts a lifetime. The neural ink used to write that memory is permanent. If you've ever had a place that just gives you the creeps for a reason you can't quite explain, what memory do you think your brain might have attached to it? Let me know your story in the comments below. This process of forging permanent memories, whether emotional or factual, relies on a stunningly elegant cellular mechanism. The very act of learning and remembering physically changes your brain, a concept known as neuroplasticity. The core process behind this is called long-term potentiation, or LTP. When two neurons communicate frequently, the connection, or synapse, between them gets stronger. Imagine a path in a forest. The first time you walk it, it's difficult. But if you walk it every day, the path becomes clearer, wider, and easier to travel. LTP is the neural equivalent. With repeated firing, the receiving neuron becomes more sensitive to the sender's signals, even sprouting new connections to make the link more robust. This isn't just a theory. Scientists can induce and observe LTP in real time. It is the physical trace of a memory, an echo of experience carved directly into the structure of your brain. Every single thing you know is encoded as a network of potentiated synapses. While we can trace the path of a memory, the ultimate mystery remains: consciousness itself. Where does our subjective awareness come from? For decades, scientists have been searching for the seat of consciousness, and one fascinating candidate is a thin, irregular sheet of neurons called the claustrum. It's tucked away beneath the cerebral cortex, and it is one of the most densely connected structures in the entire brain, with tendrils reaching out to nearly every other cortical region. It's been hypothesized to be the conductor of the orchestra, binding together all the disparate sensory inputs, sight, sound, touch, thought, into a single, unified, conscious experience. This idea gained incredible support from a study where researchers electrically stimulated the claustrum in a patient. The moment the stimulation began, the patient instantly lost consciousness. They didn't fall asleep, they simply weren't there, despite their eyes being open. The moment the stimulation stopped, they instantly regained awareness with no memory of the blank period. It's a tantalizing clue that this mysterious structure could be the switch that generates the very feeling of being you. For a long time, it was believed that we were born with all the brain cells we would ever have, but we now know this is stunningly incorrect. The brain continues to create new neurons throughout our lives, a process called adult neurogenesis, and it happens primarily in one of the deep connection hubs we've been discussing, the hippocampus. Thousands of new neurons are born here every single day. These fresh, young brain cells are thought to be particularly important for forming new memories, for learning, and for mood regulation. They are more excitable than older neurons, making them ideal for encoding new information. What's truly empowering is that you have some control over this process. Things like physical exercise, learning a new skill, and a healthy diet can significantly boost the rate of neurogenesis, while stress and lack of sleep can bring it to a grinding halt. So, the old saying, "You can't teach an old dog new tricks," is fundamentally wrong. You are literally building a new brain every single day. And perhaps the most critical process for maintaining these deep connections happens when you are completely unconscious. Sleep is not a passive state of rest for the brain. It is a highly active, essential maintenance period for memory and learning. During deep sleep, your brain gets a literal car wash. A network called the glymphatic system kicks into high gear, using cerebrospinal fluid to flush out metabolic waste products that accumulate between brain cells during the day, including the toxins associated with neurodegenerative diseases. At the same time, the brain is busy consolidating memories. The hippocampus, which recorded the day's events, begins replaying them to the cortex. This neural replay strengthens the synaptic connections associated with those memories, effectively transferring them from fragile short-term storage in the hippocampus to more durable long-term storage across the cortex. This is why a good night's sleep can help you solve a problem you were stuck on, or why you remember things more clearly after sleeping on it. Your brain is not just resting. It's filing, cleaning, and reinforcing the very fabric of your mind. Our journey into the nervous system has shown us its raw speed and power, but now we venture deeper, into the subtle, almost magical processes that define our very consciousness. For decades, it was taught as absolute gospel that you were born with all the brain cells you would ever have, and that from your first breath, it was a slow, inevitable decline. But the brain, as we're learning, loves to break its own rules. We now know that certain parts of the adult brain, particularly the hippocampus, which is crucial for learning and memory, are constantly creating brand new neurons in a process called adult neurogenesis. You are literally building a new brain day by day. This isn't just a minor biological quirk. It's a fundamental mechanism of resilience. It allows your brain to adapt to new experiences, recover from injury, and maintain cognitive function as you age. Every time you learn a new skill, engage in vigorous exercise, or even navigate a new city, you are encouraging the birth of fresh neurons ready to be wired into your neural landscape. The old static model of the brain is gone, replaced by a dynamic, regenerative wonder that is actively rebuilding itself at this very moment. And just like any bustling metropolis, this neural city generates a tremendous amount of waste. Every thought, every memory, every signal produces metabolic byproducts that, if left to accumulate, would be toxic. So how does the brain take out the trash? It has a dedicated, specialized waste clearance system called the glymphatic system. This is a relatively recent discovery that has revolutionized our understanding of brain health. While you sleep, your brain cells actually shrink, widening the spaces between them. This allows cerebrospinal fluid to pump through the brain tissue, flushing out toxins like beta amyloid plaques, which are famously associated with Alzheimer's disease. This is why a good night's sleep feels so restorative. Your brain has literally been deep cleaned. The glymphatic system is a microscopic plumbing network that operates on a nightly schedule, proving that some of the most important work your nervous system does happens when you're not even aware of it. Now, when we think of the brain's superstar regions, the wrinkled cerebral cortex usually gets all the attention. But tucked away at the back, underneath the main cerebral hemispheres, is a structure that is arguably the unsung hero of the entire nervous system, the cerebellum. Its name means little brain, which is a wild understatement. While it only accounts for about 10% of the brain's total volume, the cerebellum contains over half, and some estimates go as high as 80%, of all the neurons in your entire brain. For centuries, it was pigeonholed as the brain's motor control center, responsible for balance, coordination, and posture. And while it does that flawlessly, we now know its influence is far more profound. The cerebellum is deeply involved in processing language, regulating emotional responses, and even modulating complex cognitive tasks like planning and attention. It's the ultimate co-processor, fine-tuning not just your movements, but your thoughts and feelings, ensuring they are smooth, efficient, and appropriate for the situation. This process of fine-tuning brings us to one of the most counterintuitive marvels of brain development. We often assume that learning and growing smarter is a process of addition, gaining more neurons, more connections. But the brain often gets smarter by subtracting. This process is called synaptic pruning. When you're a toddler, your brain goes on an explosive spree of creating trillions of synaptic connections, far more than it will ever need. It's building a dense, tangled forest of possibilities. Then, beginning in childhood and peaking during adolescence, the brain begins to systematically prune away the connections that are used less frequently. The pathways that are reinforced through experience, learning, and practice are strengthened, while the weaker, unused ones are eliminated. It's a use it or lose it principle on a massive neurological scale. This sculpting process makes the brain's remaining networks far more efficient and powerful. It's also a key reason why the teenage years can be a period of such dramatic change in behavior and personality. The very architecture of their brain is undergoing a massive and critical renovation. This brain architecture isn't just for processing our own actions, it's also built to understand the actions of others. And it does this through a truly remarkable class of brain cells known as mirror neurons. These neurons fire when you perform an action, like picking up a cup of coffee. But what's astonishing is that the very same neurons fire when you simply watch someone else pick up a cup of coffee. Your brain, on a cellular level, simulates their action as if you were doing it yourself. This neural mirroring is thought to be a fundamental building block of empathy, allowing us to understand the intentions and feel the emotions of others. When you see someone smile and you feel a glimmer of their joy, or you wince when you see someone trip, that's your mirror neuron system at work. It's the neurological basis for imitation, social learning, and the deep instinctual connection we feel with other people. It makes you wonder, how much of our compassion is a conscious choice, and how much is hardwired into us? Let me know in the comments what you think is the true source of human empathy. The brain's ability to map our reality is so powerful that it can persist even when that reality changes dramatically. This is powerfully demonstrated by the phenomenon of phantom limb sensation. When a person has a limb amputated, the vast majority continue to feel vivid, detailed sensations, like an itch on a wrist that isn't there, or the clenching of fingers that are gone. This isn't imagination, it's a neurological reality. In the brain's somatosensory cortex, there is a detailed map of the entire body, a homunculus, where different areas of tissue are dedicated to processing sensation from specific body parts. When a limb is removed, the corresponding area on that brain map doesn't just go dark. The neurons remain, and without any input from the missing limb, they can become hyperactive or be stimulated by neighboring cortical regions. So when the area of the brain map for the face, which is next to the hand area, is stimulated, it can trigger the sensation of a touch on the missing hand. It's a haunting and profound example of how our entire experience of our body is a construct, a detailed simulation running inside the brain. With all these intricate and delicate systems at play, from generating new cells to mapping phantom limbs, the brain must be fiercely protected. It operates within a fortress, guarded by one of the most exclusive security systems in the universe, the blood-brain barrier. This isn't a single wall, but a highly selective, semi-permeable border of endothelial cells lining the capillaries in the brain. These cells are packed together with incredibly tight junctions, creating a physical barrier that prevents toxins, pathogens, and most drugs circulating in your bloodstream from entering the sensitive neural environment of the central nervous system. It's incredibly effective at keeping the brain safe, but it also presents a huge challenge for medicine, as it blocks many potentially life-saving drugs from reaching their targets in the brain. Specialized molecules like glucose and certain amino acids are actively transported across by specific proteins, like VIPs being escorted past the velvet rope at an exclusive club. This biological fortress ensures the brain's electrochemical environment remains perfectly stable, allowing the marvels we've just explored to continue their work, uninterrupted by the chaos of the outside world. Your brain is the most complex, energy-hungry, and irreplaceable object in the known universe. It's also incredibly soft and vulnerable, with the consistency of firm tofu. So how does this delicate masterpiece survive a lifetime of bumps, jolts, and microscopic invaders inside your skull? The answer is a security system so sophisticated it would make a fortress designer weep with envy. And we're about to take a tour of its most amazing defenses. If you're fascinated by the hidden world inside our heads, hit that subscribe button and let's pull back the curtain. We begin with the first line of defense, a triple-layered suit of biological armor called the meninges. This isn't just one simple covering, it's a trio of membranes, each with a specific job. The outermost layer, right under the skull, is the dura mater, which is Latin for tough mother, and it lives up to its name. It's made of dense, fibrous tissue, like a leather cap protecting the brain from rubbing against the hard bone of the skull. Beneath that is the arachnoid mater, or spider-like mother, named for its delicate, web-like extensions that reach down to the next layer. This web creates a space, the subarachnoid space, which isn't empty. It's filled with a special fluid we'll get to in a moment. Finally, hugging the brain's every curve and contour is the pia mater, the tender mother. This layer is so thin and delicate it's practically transparent, yet it's absolutely vital, carrying blood vessels that nourish the brain tissue itself. Together, these three mothers form a comprehensive, shock-absorbing helmet worn on the inside. Now, about that fluid filling the space created by the arachnoid web. This is cerebrospinal fluid, or CSF, and it's one of the most incredible substances in your body. Your entire brain and spinal cord are suspended in it, literally floating. This buoyancy is a game changer. A typical adult brain weighs about 1,400 grams, or 3 pounds. But floating in CSF, its effective weight is reduced by about 97% to a mere 50 grams. This prevents the brain's own weight from crushing the nerve connections and blood vessels at its base. But it's more than just a flotation tank. The CSF acts as a liquid cushion, absorbing shocks from everyday movements like jogging or even just nodding your head. And perhaps most astonishingly, it functions as the brain's private waste disposal system. While you sleep, the channels in your brain actually expand, allowing CSF to flush out metabolic toxins and cellular debris that build up during the day. You produce about half a liter, or a pint, of this crystal clear fluid every single day, completely replacing the entire volume in your head 3 to 4 times over. This intricate system of physical barriers is brilliant, but what about microscopic threats from within our own bodies? The bloodstream is full of hormones, chemicals, and the occasional pathogen that could wreak havoc on the brain's precise chemical environment. To counter this, the brain deploys its most exclusive defense, the blood-brain barrier. This isn't a wall in the traditional sense. Instead, it's a highly specialized and tightly packed layer of endothelial cells lining the capillaries in the brain. The junctions between these cells are so tight they form a near impenetrable seal. This barrier is the ultimate bouncer, scrutinizing everything that tries to pass from your blood into your brain tissue. It actively transports essential molecules like glucose, oxygen, and certain amino acids across, while physically blocking toxins, pathogens, and most large molecules. It's so effective, in fact, that it poses a major challenge for modern medicine. An estimated 98% of all potential drugs for brain disorders are blocked by it, making it incredibly difficult to deliver therapies for conditions like brain cancer or Alzheimer's. If you could design a new feature for the brain's defense system, what would it be? Let me know your creative ideas in the comments. But what if something does get past the outer defenses? Or if a neuron simply dies of old age? The brain can't rely on the body's general immune system, as a full-blown inflammatory response would be catastrophic in such a confined space. So it has its own private, highly specialized immune cells called microglia. These cells are the brain's diligent janitors, paramedics, and security guards all rolled into one. In their resting state, they have long, spindly arms that constantly reach out and survey their local environment, checking on the health of nearby neurons and synapses. If they find cellular debris, plaques, or a dead neuron, they transform, retracting their arms to become blob-like amoeboid shapes. They then crawl to the site and perform phagocytosis, literally eating the debris to keep the neural environment clean. But if they detect a pathogen or severe injury, they switch to attack mode, releasing chemicals that trigger a controlled inflammatory response to neutralize the threat. They are the unsung heroes maintaining order in the complex city of the brain. For centuries, it was a biological dogma that you were born with all the brain cells you would ever have, and that once a neuron was gone, it was gone forever. This idea was so entrenched it was taught as absolute fact. We now know it's spectacularly wrong. The brain actually can and does create new neurons throughout adulthood, a process called adult neurogenesis. While it doesn't happen everywhere, it's been definitively observed in at least 2 key areas. One is the olfactory bulb, which processes smells. The other, more famous location is the hippocampus, a region absolutely critical for learning and forming new memories. Thousands of new neurons are born here every single day. This process is thought to be fundamental to our ability to learn, adapt, and even regulate our mood. And here's the kicker: you have some control over it. Activities like sustained aerobic exercise, learning new skills, and living in an enriched environment have all been shown to significantly boost the rate of neurogenesis. So the next time you go for a run, you're not just exercising your body, you're literally building a better brain. Have you ever wondered what happens in your brain when you sleep? The cleanup crew we just talked about is a huge part of it. What's the weirdest dream you remember having? While the brain's ability to create new neurons is limited,
The nerves outside your brain and spinal cord, the peripheral nervous system, possess a truly remarkable capacity for repair. If you get a deep cut on your finger and sever a nerve, you might lose sensation, but with time, it can often return. This is thanks to an incredible regeneration process that the central nervous system just can't manage. When a peripheral nerve axon is cut, the part disconnected from the cell body dies off. But the support cells that insulated it, called Schwann cells, remain. They don't just sit there, they go to work. They clean up the debris of the dead axon and then form a structure called a band of Bungner, essentially a hollow tube or a physical scaffold that creates a perfect pathway for a new axon to grow. The surviving end of the neuron then sprouts a new axon tip, which navigates down this Schwann cell tunnel, growing about 1 millimeter per day until it reconnects with its original target, restoring function. This is why a surgeon can reattach a severed limb, and with luck and time, a person can regain movement and feeling. So, if the peripheral nervous system is so good at repairs, why are spinal cord injuries so devastating and often permanent? The answer lies in a fascinating and tragic biological trade-off. When the brain or spinal cord, the central nervous system, is injured, a different type of support cell called an astrocyte rushes to the site of the damage. Their goal is to quarantine the injury immediately, preventing inflammation and toxic chemicals from spreading and causing a cascade of neuron death. They do this by multiplying rapidly and forming a dense, tangled network of cellular processes. This structure is known as a glial scar. In the short term, this is a life-saving defense mechanism, walling off the damage. But in the long term, this very scar that saved the surrounding tissue becomes a major problem. It forms a thick, impenetrable physical barrier that a regenerating axon simply cannot push through. The same protective instinct that contains the initial damage actively blocks any hope of long-term repair, a perfect example of a biological double-edged sword. This difference in repairability between the central and peripheral systems is a huge area of research. What future medical breakthrough are you most excited about? The brain's self-protection can sometimes get in the way of healing. Can you think of any other examples in life where a defense mechanism can also cause problems? From its triple-layered armor and personal flotation device to its exclusive bouncers and dedicated cleanup crews, the brain's protective systems are a marvel of evolutionary engineering. It's a constant, silent battle being waged to keep your mind safe, clear, and functional. Every thought you have, every memory you cherish, is made possible by this incredible, multi-layered fortress. We've explored how the brain protects itself, but what happens when these systems go wrong? Join us next time as we delve into the world of neurological disorders. Make sure you're subscribed with notifications on so you don't miss it. And if you learned something new today, give this video a like. Thanks for watching. What if I told you that your most cherished childhood memory might have never happened? Not a single part of it. Your brain, the most sophisticated storytelling machine in the universe, might have simply invented it. We think of our memories as perfect, pristine recordings of the past, but the biological truth is far stranger, more flexible, and infinitely more fascinating. Today, we're unlocking the blueprint of memory itself, exploring how our brains build, break, and rebuild our personal histories. And it all starts with that unsettling idea: our memories are not always real. The brain can, and often does, create entirely false memories. These aren't just fuzzy details. They can be vivid, emotionally charged, and highly detailed recollections of events that never took place. Neuroscientists have shown that through suggestion, or even just the act of imagining an event, our brains can weave these fictions into the fabric of our personal timeline. The same neural machinery used to recall a real event is activated when constructing a false one, making it feel completely authentic to us. It's a powerful reminder that memory isn't a video camera.
It's a creative editor constantly working to build a coherent but not always accurate story of our lives. This malleability is a fundamental feature, not a bug, allowing us to learn and adapt. But it also means our internal world is a delicate tapestry, susceptible to being rewoven. So, if memories can be false, what makes them feel real in the first place? What are they even made of? The answer isn't in a file or a folder, but in the connections between your neurons. The physical basis for a long-term memory is a process called synaptic plasticity, specifically long-term potentiation, or LTP. When you learn something new, certain neurons fire together. The more they fire together, the stronger their connection, or synapse, becomes. Think of it like forging a new path in a dense forest. The first time you walk it, it's difficult. But with each trip, the path becomes clearer, wider, and easier to travel. That strengthened pathway is the memory. A single complex memory, like your first day of school, isn't stored in one spot. It's a distributed network of thousands or even millions of these strengthened synapses spread across different regions of the brain. A vast, interconnected web representing the sight, sound, and feeling of that moment. But how does your brain manage this colossal library of pathways? It needs a master librarian, an index system to keep everything organized. That role is played by a seahorse-shaped structure deep in your temporal lobe called the hippocampus. Crucially, the hippocampus does not store long-term memories itself. Instead, it acts like a temporary hub and a meticulous indexer. When you experience something, the hippocampus gathers all the separate sensory inputs, what you saw, heard, felt, and binds them together into a single, cohesive episode. It then directs the consolidation process, gradually transferring this memory from its own temporary storage to more permanent locations throughout the cerebral cortex. This is why individuals with hippocampal damage can often remember their distant past perfectly, but are unable to form any new long-term declarative memories. They can experience a moment, but their brain's librarian is unable to catalog it for future retrieval. It's an incredible system, but imagine if you could choose which part of that system to upgrade. If you could enhance one specific type of memory, like instantly recalling names, mastering new languages, or never forgetting a face, what would you pick? Let me know your dream memory superpower in the comments below. Now, here's where the blueprint of memory gets truly wild. Every time you access a memory, you aren't just passively viewing it, you are actively reconstructing it. This process, known as memory reconsolidation, makes the memory temporarily unstable and vulnerable. For a brief window of time after recall, that neural pathway becomes malleable again. During this period, the memory can be updated with new information, colored by your current emotional state, or linked to new experiences before it is resaved or reconsolidated. This is a profound concept. It means your memories of the past are not static relics. They are living documents that you edit slightly every single time you read them. This explains why our perspective on past events can shift over time, as we reinterpret them through the lens of new wisdom and experiences. The memory you have of an event today is not the exact same memory you had of it 10 years ago. So how does the brain handle this constant flood of experiences, deciding which ones are important enough to be consolidated and which can be discarded? A huge part of this critical work happens when you're not even conscious, during sleep. While you rest, your hippocampus is hard at work. It replays the neural firing patterns of significant events from the day, like a director rewatching the daily footage. This replay, happening at a much faster speed, strengthens the synaptic connections associated with those memories in the cortex, effectively transferring them into long-term storage. At the same time, the brain engages in synaptic pruning, weakening the connections of trivial information.
This is why pulling an all-nighter to cram for an exam is often counterproductive. You're denying your brain the essential downtime it needs to actually file away what you've just learned. Sleep isn't just rest, it's the brain's graveyard shift for memory management.
Of course, not all memories are created equal. The brain uses entirely different systems for different types of information. We have our declarative memories, the what of our lives. These are the facts, figures, and personal events you can consciously recall, like the capital of France or what you had for breakfast. But there's another, more mysterious system, procedural memory. This is the how.
It's the memory of skills and habits stored in areas like the cerebellum and basal ganglia. Riding a bike, typing on a keyboard, or playing a musical instrument are all procedural memories. You perform them automatically without conscious thought about the individual steps.
This is why a person with severe amnesia who can't remember their own name might still be able to play the piano flawlessly. Their declarative memory system is damaged, but their procedural system remains perfectly intact, a ghost of learned skills operating beneath the surface of their conscious mind. And finally, let's talk about the most potent memory trigger of all, a smell.
Have you ever caught a whiff of something, freshly cut grass, a specific perfume, baking cookies, and been instantly transported back to a powerful, emotionally charged moment from your distant past? This phenomenon is so distinct it has a name, the Proust effect, and there's a clear neurological reason for it.
The olfactory bulb, the brain structure that processes smells, has uniquely direct and intense connections to two key areas: the amygdala, our emotional processing center, and the hippocampus, our memory indexer. Information from our other senses, like sight and sound, takes a more indirect route.
This special, privileged neural highway for scent is why a smell can unlock a flood of vivid memories and emotions more rapidly and powerfully than almost any other sensory cue, providing a direct, unfiltered gateway to our past. What if I told you that every single thought, every emotion, and every memory you've ever had wasn't just a spark of electricity, but a complex and beautiful conversation? A conversation spoken in a language of over 100 different chemical words. These are the couriers of your mind, delivering messages at unimaginable speeds to write the story of who you are. We often think of the brain as a purely electrical computer, but the real magic happens in the spaces between the neurons. These tiny gaps, called synapses, are bustling chemical marketplaces where information is translated and transformed. And the currency of this marketplace? Neurotransmitters. Let's start with one you've definitely heard of, but probably don't fully know. Serotonin is famously nicknamed the happy chemical, responsible for feelings of well-being and contentment. But here's the twist. A staggering 95% of your body's serotonin isn't in your brain at all. It's in your gut. Your gastrointestinal tract is lined with millions of nerve cells, forming what scientists call the second brain. Here, serotonin is a master regulator, controlling the rhythmic contractions of your intestines, signaling pain, and even managing your appetite. This is why your mood and your gut health are so deeply intertwined. The chemical that helps you feel happy upstairs is the same one running the entire complex operation downstairs. From the chemical of contentment, we move to the chemical of craving. You've probably heard dopamine called the pleasure molecule, released when you eat a delicious meal or win a game. But that's a huge oversimplification. Dopamine is actually the motivation molecule. Its primary job isn't to give you pleasure, but to make you want things. It's the anticipation of the reward, not the reward itself, that truly gets dopamine flowing. It's the neurochemical engine that drives you to seek out food, achieve goals, and learn new skills. Think of it as the difference between enjoying a gift and the thrilling excitement you feel while unwrapping it.
dopamine is the feeling of unwrapping, the forward-leaning drive that keeps us striving, exploring, and moving toward a potential reward. It's what got our ancestors to hunt for one more berry patch, and it's what gets you to scroll for one more video. But how did we even discover these invisible messengers? The story of the very first neurotransmitter identified is like something out of a dream, because it was. In 1921, a scientist named Otto Loewy woke up with a brilliant experimental design fully formed in his mind. He rushed to his lab and took 2 living frog hearts, keeping them beating in a saline solution. He stimulated the vagus nerve of the first heart, which he knew would slow its beat. Then he took some of the fluid from that heart's container and applied it to the second heart. Incredibly, the second heart also began to slow down, proving that the nerve wasn't just sending an electrical signal, but was releasing a chemical substance. He called this substance vagus stuff, and we now know it as acetylcholine, the crucial neurotransmitter that, among many other things, commands your muscles to contract every time you move. So we have chemicals that regulate mood, drive motivation, and make us move. But what about the opposite? What stops the brain from firing on all cylinders, all the time? Meet GABA, or gamma-aminobutyric acid. If your brain is a car, GABA is the brake pedal. It's the primary inhibitory neurotransmitter in your central nervous system, meaning its job is to calm things down, reduce neuronal excitability, and prevent signals from overwhelming your brain. Without sufficient GABA, your brain's electrical activity could spiral out of control, leading to anxiety, restlessness, and even seizures. Every moment of calm focus, every night of restful sleep, you have GABA to thank for gently tapping the brakes and keeping your mind from racing into chaos. What's your go-to activity to calm your mind and get that GABA flowing? Let us know your favorite relaxation technique in the comments below. Of course, a car with only a brake pedal won't get you very far. You also need an accelerator. In the brain, that accelerator is glutamate. It is by a huge margin the most abundant excitatory neurotransmitter, present in over 90% of all synaptic connections. Glutamate is the workhorse of your brain, a universal on switch that kicks neurons into action. It's absolutely essential for learning and memory. When you learn something new, the connections between your neurons strengthen, and glutamate is the chemical that orchestrates this process, effectively carving memories into your neural pathways. But this powerful accelerator has a dark side. In excessively high concentrations, such as after a stroke or brain injury, glutamate becomes toxic. It can overexcite neurons to the point that they literally work themselves to death in a destructive process called excitotoxicity. Beyond the basic on-off switches, your brain produces its own specialized drugs for specific situations. When you experience intense physical stress or pain, your nervous system releases a class of neurotransmitters called endorphins. The name itself is a clue. It's a mashup of endogenous, meaning from within the body, and morphine. That's right, your brain manufactures its own private supply of opiates. These molecules are structurally similar to powerful pain-relieving drugs, and they work by binding to the same opioid receptors in your brain, effectively blocking pain signals. This is the incredible mechanism behind the phenomenon known as a runner's high, where the physical stress of prolonged exercise triggers a flood of endorphins, creating a feeling of euphoria and analgesia that allows athletes to push past their pain thresholds. Finally, we arrive at a chemical that builds bridges not between neurons, but between people. It's often called the love hormone or the cuddle chemical, but oxytocin is far more complex than that. Released during childbirth, nursing, and physical touch, oxytocin is fundamental to forming social bonds, fostering feelings of trust, and promoting empathy. It's the warm, fuzzy feeling you get when hugging a loved one. But research reveals a surprising duality to this bonding agent. While oxytocin enhances positive feelings towards your in-group, your family, your friends, your team, it can simultaneously increase defensiveness and suspicion towards those you perceive as outsiders. It strengthens the feeling of us, but can also sharpen the line that creates a them. It's a powerful reminder that the chemicals shaping our most profound feelings of connection are the very same ones that can draw the boundaries between us. Imagine building a city more complex than any on Earth, not over centuries, but in just a few months. Now imagine doing it while you're asleep. Your brain did exactly that before you were even born. It's a biological marvel that's constantly under construction, a masterpiece of engineering where the blueprints are written in DNA and the building materials are the very essence of life. To truly appreciate this brilliance, we have to look at the microscopic architects and the cellular masons at work. If you're fascinated by the raw, creative power of your own nervous system, make sure you're subscribed, and let's dive into the build. The construction boom starts early, and it is staggeringly fast. During peak development in the fetal brain, neurons are generated at an almost unbelievable rate. We're talking about the creation of roughly 250,000 new nerve cells every single minute. This process, called neurogenesis, is so explosive that by the time a baby is born, its brain contains the vast majority of the neurons it will ever have, around 86 billion of them. This isn't just random cell division, it's a carefully orchestrated migration. These brand new neurons travel from their birthplace deep within the brain to their final destinations, forming the foundational layers of the cortex and other critical structures. It's an over-the-top, build everything at once strategy, creating a dense, tangled jungle of potential that sets the stage for everything to come. But creating this much raw potential comes with a challenge. It's incredibly inefficient. The infant brain is a chaotic network of redundant connections. To sculpt this jungle into a finely tuned processing machine, the nervous system employs a strategy that sounds destructive but is actually a stroke of genius: synaptic pruning. Starting in early childhood and continuing through adolescence, the brain begins to systematically eliminate unused or weak connections between neurons. It's like a master gardener trimming away overgrown branches to allow the stronger ones to flourish. This process is guided by experience. The connections you use, for language, for movement, for recognizing faces, get stronger. The ones you don't, wither away. It's a literal use it or lose it principle, and it's why the brain of a teenager can be more powerful and efficient than that of a toddler, even with fewer overall connections. This refinement carves out the unique neural pathways that define who you are. It's not just about removing old wires, though. It's also about upgrading the ones you keep to make them lightning fast. This upgrade is called myelination, and it's one of the most critical processes for building a brilliant mind. Many of your nerve fibers, or axons, are wrapped in a fatty, insulating substance called a myelin sheath. This sheath isn't continuous, it has tiny gaps. Instead of traveling smoothly down the axon, an electrical signal effectively jumps from one gap to the next, a process called saltatory conduction. This biological cheat code can increase the speed of a nerve impulse by up to 100 times. Myelination begins before birth but continues well into your 20s, particularly in the prefrontal cortex, the seat of judgment and decision-making. The development of complex skills, from playing a piano concerto to mastering a new language, is physically reflected in the brain as a thickening of the myelin around the relevant neural circuits, turning sluggish connections into superhighways of thought. Now, for decades, neurons got all the glory. They were the stars of the show, the thinkers, the messengers. But they are massively outnumbered by their support crew, the glial cells. For every one neuron, there are at least as many, and in some brain regions, up to 10 times as many glial cells. We used to think of them as simple cellular glue. The word glia literally means glue. just there to hold the important neurons in place. We couldn't have been more wrong.
Glial cells are the unsung heroes of the nervous system. Astrocytes, a star-shaped type of glia, provide nutrients to neurons, maintain chemical balance, and are even involved in repairing the brain after injury. Microglia act as the brain's dedicated immune system, hunting down pathogens and cleaning up dead cells.
Oligodendrocytes are the cells that actually produce the myelin sheath in the central nervous system. We're now discovering they do even more, actively participating in synaptic communication and modulating neural activity. They are not just the support crew, they are co-pilots in the cockpit of your mind. What's a function you used to think was simple, but turned out to be incredibly complex? Let me know in the comments below. This brings us to one of the most exciting reversals in modern neuroscience. The old dogma was that you were born with all the brain cells you'd ever have, and that from adulthood onward, it was all downhill. This has been proven definitively false.
While widespread neurogenesis like that in the womb doesn't happen, your adult brain absolutely can and does create new neurons in a process called adult neurogenesis. This remarkable ability is largely confined to two specific areas. One is the olfactory bulb, related to your sense of smell.
The other, and far more studied, is the hippocampus, a region absolutely vital for learning and memory formation. Every day, your brain creates hundreds of new neurons in the hippocampus that can then be integrated into existing circuits. And what stimulates this growth? Things like physical exercise, enriched environments, and active learning. So, the very act of challenging your brain can help it build the new components it needs to keep learning. Of course, you can't have this brilliant, ever-changing city without some serious security at the gates. The brain is the body's most sensitive and energy-hungry organ, and it needs extreme protection from toxins, pathogens, and fluctuating chemical levels in the blood. This protection is provided by the blood-brain barrier. It's not a single wall, but a highly selective, semi-permeable border of endothelial cells that line the capillaries in the brain. The junctions between these cells are fused so tightly that they prevent most substances from passing from the bloodstream into the delicate brain tissue. Only very specific molecules, like oxygen, glucose for energy, and certain amino acids, are actively transported through by special protein escorts. This barrier is so effective that it poses a major challenge for medicine. Many potentially life-saving drugs can't get past its security, forcing scientists to develop ingenious ways to smuggle therapies into the brain. So we have the builders, the remodelers, the support crew, and the security. But how does this intricate structure actually learn? How does an experience, a fact, or a skill become a permanent part of the brain's architecture? The answer lies in a principle often summarized as neurons that fire together, wire together. This process is called long-term potentiation, or LTP. When one neuron repeatedly sends a signal to another, the connection, or synapse, between them physically strengthens. The receiving neuron becomes more sensitive to the signals from the sending neuron. It might sprout more receptors or release its signals more reliably. This makes it more likely that they'll fire together in the future. LTP is the cellular mechanism of memory. Every time you recall a memory or practice a skill, you are initiating LTP and reinforcing that specific neural circuit. It's not just an abstract concept, it's a physical change, a microscopic rewiring that turns a fleeting thought into a lasting piece of your identity. Imagine a future where you could type an email just by thinking it, or move a robotic arm on the other side of the world with a mere thought. This isn't science fiction. This is the new reality being built at the final frontier of neuroscience, and it's where we're headed right now. We've explored the vast, intricate network that makes you. But now we venture into the unknown, the very edge of our understanding, where science is rewriting what we thought was possible for the human mind.
The breakthroughs happening today are not just changing medicine, they're changing the definition of what it means to be human. For instance, the very idea of connecting our brains directly to computers is no longer confined to Hollywood. We now have brain-computer interfaces, or BCIs. These remarkable devices can read the electrical signals of your neurons and translate them into commands. Tiny electrode arrays, some smaller than a postage stamp, can be implanted in the brain to listen in on the motor cortex's conversation. For individuals with paralysis, this technology is already life-changing, allowing them to control advanced prosthetic limbs, move a cursor on a screen, and even regain a sense of touch through feedback systems that send signals back into the brain. The communication is becoming a two-way street. But what if, instead of interfacing with external machines, we could supercharge the brain's own ability to repair and rebuild itself? For over a century, the dogma was that you were born with a finite number of brain cells. Lose them, and they were gone forever. This has been proven spectacularly wrong. The discovery of adult neurogenesis reveals that our brains can and do create new neurons throughout our lives, a process primarily occurring in the hippocampus, a region critical for learning and memory. This isn't just a tiny, insignificant effect. Thousands of new brain cells can be born every single day, and the best part? You can influence it. Activities like vigorous exercise, continuous learning, and even navigating new and complex environments have been shown to boost the rate of neurogenesis, forging new pathways and enhancing cognitive resilience. It's a powerful reminder that our brains are not static hardware, but dynamic, living tissue that we can actively cultivate. Growing new neurons is incredible, but what if scientists could seize control of specific neural circuits with the flick of a switch? This is the breathtaking reality of a technique called optogenetics. It sounds like something from a fantasy novel. Researchers take a gene from light-sensitive algae, a gene that creates a protein acting like a tiny solar panel. They then insert this gene into specific neurons in a living brain using a harmless virus as a delivery vehicle. The result? Those targeted neurons now become responsive to light. Scientists can then shine a laser through a hair-thin fiber optic cable and instantly activate or deactivate that exact set of cells. This gives them an unprecedented ability to turn behaviors, memories, or emotional states on and off with pinpoint precision, allowing us to finally draw a direct line from the firing of a specific neural circuit to a complex action. What's the one brain function you'd want to understand if you could activate the neurons responsible for it at will? Share your most creative ideas in the comments below. While we're busy trying to master the brain's electrical signals, it turns out the brain has a secret plumbing system we only just discovered in 2012. It's called the glymphatic system, and it acts as the brain's dedicated waste disposal service. During the day, your brain cells are hard at work, and just like any busy city, they produce a lot of metabolic trash. But when you fall into a deep sleep, something amazing happens. Your brain cells actually shrink slightly, widening the channels between them. This allows cerebrospinal fluid to be pumped through the brain tissue, flushing out toxic proteins and waste products that have accumulated. One of the key toxins it clears away is beta amyloid, the protein that clumps together to form the infamous plaques in Alzheimer's disease. This discovery provides the strongest biological reason yet for why sleep is not a luxury, but a non-negotiable, essential maintenance period for your long-term brain health. Cleaning the brain is one thing, but to truly understand it, some scientists have undertaken a mission of almost unimaginable scale, mapping its every connection. This grand endeavor is called connectomics. The goal is to create a complete wiring diagram of the human connectome. Think about that. Your brain has around 86 billion neurons, and each neuron can have thousands of connections or synapses with other neurons. The total number of connections is estimated to be around 100 trillion. To put that in perspective, there are more synaptic connections in your single brain than there are stars in the Milky Way galaxy. Mapping this network is a monumental task, requiring petabytes of data from high-resolution imaging and massive supercomputers to reconstruct the circuits. If we succeed, this map could unlock the secrets of consciousness, personality, and the precise origins of neurological disorders. Mapping the brain's physical structure is one colossal frontier. Another is mapping how that intricate wiring gives rise to our most profound and uniquely human experiences, like our perception of art and beauty. This is the fascinating field of neuroaesthetics. Using tools like fMRI, scientists are peering into the brain as a person listens to a moving piece of music, reads a beautiful line of poetry, or gazes at a masterpiece of art. They've found that these experiences aren't just processed in one single art center. Instead, they light up a whole network of brain regions, including those involved in emotion, pleasure, and our sense of self, particularly the default mode network. This research suggests that our appreciation for beauty is deeply wired into the core systems that govern our survival and our identity, linking our highest artistic aspirations to our most fundamental neural architecture.
And in a stunning, full-circle moment, as we use our brains to understand art and science, we're also using what we learn to build artificial intelligence, which is now, in turn, helping us understand the brain. This symbiotic relationship between neuroscience and AI represents one of the most exciting frontiers in all of science. Early AI was directly inspired by the brain's structure of neurons and synapses, leading to the creation of artificial neural networks. Today, these networks are incredibly sophisticated. AI models can now analyze the massive, complex datasets from connectomics or fMRI scans far faster and more effectively than any human could, identifying patterns that were previously invisible. We are now building AI simulations of specific brain circuits to test hypotheses about how memory or vision works, creating a powerful feedback loop where the study of the biological brain improves the artificial one, and the artificial brain accelerates our understanding of the biological. We are building models of our minds to better know ourselves, pushing into a future where the line between natural and artificial intelligence is becoming increasingly blurred. Every star you see, every song you hear, every memory you cherish, none of it exists as you experience it. It's all a grand illusion, a story being written and read at the same time by the 3-pound universe inside your head. We've journeyed from single neurons to the sprawling networks that create our every thought. Now, for our final exploration, we're diving into the deepest, most mind-bending truths about the command center of your reality. Let's shatter a fundamental idea of how you perceive the world. You probably think your brain is a passive receiver, that your eyes see, your ears hear, and your brain just processes it all as it comes in. But the truth is profoundly stranger. Your brain is not a reactor, it's a predictor. It operates as a prediction engine, constantly building a sophisticated model of reality based on past experiences. What you perceive as the present is actually your brain's best guess about what's happening. The sensory information flooding in from your eyes and ears doesn't create your reality. It just serves to correct the errors in your brain's prediction. When the incoming data doesn't match the prediction, you feel surprise. This is why optical illusions work so well. They exploit the shortcuts and assumptions your brain uses to build its predictive model. Your entire conscious experience is less like a live video feed and more like a beautifully edited movie, directed and produced by your own brain, milliseconds ahead of the action. For centuries, we believed a devastating truth, that you were born with all the brain cells you would ever have,
and that from adulthood on, it was a slow, inevitable decline. But this piece of dogma has been completely overturned. Your brain possesses the remarkable ability of neurogenesis, the creation of brand new neurons well into old age. This process is most active in the hippocampus, a region critical for learning, memory, and emotional regulation. Factors like vigorous exercise, a stimulating environment, and continuous learning can significantly boost the birth rate of these new cells. So, far from being a static organ, your brain is a dynamic, living system capable of regenerating and rewiring itself throughout your entire life. You are not just protecting what you have, you are actively building a better brain every single day. Of course, growing new brain cells is incredible, but keeping the 86 billion you already have safe is a top priority, 24/7 job. And for that, your brain has the most exclusive security detail in the universe, the blood-brain barrier. This isn't a physical wall, but a highly selective, semi-permeable border of endothelial cells that line the capillaries in your brain. It acts like the ultimate bouncer, meticulously controlling what gets in and what stays out. It allows essentials like oxygen, glucose, and certain amino acids to pass through, while blocking toxins, pathogens, and most drugs from entering the brain's delicate environment. This incredible protective filter is why brain infections are relatively rare, but it's also a double-edged sword. It's so effective that it prevents about 98% of potential therapeutic drugs from reaching their target, making it a massive challenge for scientists trying to treat diseases like brain cancer or Alzheimer's. Protecting the brain is one thing, but what about connecting with it directly? For decades, it's been the stuff of science fiction, but we are now living in the era of the brain-computer interface, or BCI. These are systems that create a direct communication pathway between the brain's electrical activity and an external device. It's happening right now. Paralyzed individuals can now control robotic arms with their thoughts, moving them with a dexterity that was previously unimaginable. People who have lost the ability to speak can type out messages on a screen simply by thinking of the letters. These aren't just lab experiments anymore. They are real-world applications restoring function and independence. The technology works by implanting electrodes that can read the signals from motor cortex neurons and using complex algorithms to translate those intentions into digital commands. The line between mind and machine is blurring faster than anyone thought possible. The idea of controlling things with our minds is becoming reality. What's one thing you would control with just a thought? Let me know down below, so we can see the brain in action, protecting itself, even interfacing with machines. But what is it doing when you're, well, doing nothing? When you're just sitting, daydreaming, letting your mind wander? It turns out your brain is anything but idle. During these moments of quiet repose, a specific network of brain regions, known as the default mode network, roars to life. This network, which spans parts of the prefrontal cortex, the temporal lobe, and the parietal lobe, is your brain's me-time circuit. It's deeply involved in introspective thought, thinking about yourself, remembering your past, and imagining your future. It's the neural basis for your sense of self, your autobiography. When you snap to attention to focus on a task, the default mode network deactivates, and task-oriented networks take over. This constant toggling between outward focus and inward reflection is a fundamental rhythm of conscious thought, giving you the ability to both interact with the world and understand your place within it. This internal world of belief and self-reflection is so powerful that it can create profound physical changes in your body, a phenomenon we see most clearly in the placebo effect. This is far more than just mind over matter. When a person believes they are receiving a real medical treatment, even if it's just a sugar pill, their brain can orchestrate real, measurable physiological changes. For example, a placebo can trigger the brain to release its own powerful, internally produced painkillers called endorphins, which bind to the same receptors as opioid drugs. Brain scans show that when a person takes a placebo for pain, the pain processing regions of their brain actually become less active. This effect isn't limited to pain. It has been shown to reduce symptoms in conditions ranging from Parkinson's disease by prompting the release of dopamine to depression and anxiety. It's a stunning demonstration that your expectations and beliefs housed in the neural networks of your brain are not separate from your physical health. They are an integral and powerful component of it. And that brings us to our final and perhaps most profound truth. We've talked about predictions, neurons, barriers, and beliefs. But what does it all add up to? The ultimate function of your nervous system is to build your reality. The entire world you experience is a construction. The colors you see don't actually exist out in the world. They are the result of your brain interpreting different wavelengths of electromagnetic radiation. The sounds you hear are just your brain's interpretation of vibrating air molecules. The solidness of the table you touch is an illusion created by the electrical repulsion between atoms, translated into a sensation by your brain. Every sight, every sound, every emotion, every thought is a translation, an electrochemical story woven together in the dark, silent theater of your skull. You are not a window looking out at the world. You are the artist painting the world on the inside of your own mind. That 3 pounds of tissue between your ears is not just in the universe. In a very real sense, the universe, as you will ever know it, is in it. From the lightning-fast spark of a single neuron to the grand, intricate masterpiece of human consciousness, we've seen how this incredible system defines our existence. Thank you for joining this journey through the most amazing facts about the nervous system. If you feel a little more in awe of the universe inside you, make sure to hit that like button, subscribe, and ring the notification bell so you don't miss what we explore next.